with the barest introduction into, this is the sky and here's the moon and all of that. Now we're into the level of cosmology, which is kind of the summation of astronomy. In fact, if we went any further, it would pretty much lead into theology. So there's, at one point this evening, I'm going to make a few parenthetical comments that you might think are on the other side of the astronomy theology line, but they are not officially part of the short course, but I've, in my 71 plus years, I've done some thinking about this and wanted to, in case you're thinking along those lines, we can kind of share some thoughts on that. First, we need to see about how to measure cosmological distances. First, we got to be able to measure things within the solar system and throughout the rest of our galaxy. And we've gone over this 2 or 3 times during the short course, kind of overlapping. So chapters 8 and 9 in your book will have a lot of information in there. For those of you who weren't with us then and haven't looked at the online presentations yet, we'll very quickly go over a crash version of how we measure distances within the Milky Way galaxy using parallax. The concept that nearby, relatively near objects seem to shift back and forth when we change our vantage point with respect to more distant objects. The classic demonstration of that is closing one eye and then the other as you hold your finger in front of your face, and your finger seems to jump back and forth against the background of things and people farther away in the room. And if we measure that, we can see how far away things are using a little bit of trigonometry. The problem is, and some of the smartest of the ancients, like Aristotle, figured the Earth didn't move because this parallax of nearer stars compared to farther ones is so incredibly small. The very nearest stars don't even have a parallax of 1 second of arc, a 3600th of a degree. So they ruled out that the Earth was moving around the sun because they couldn't observe any parallax. But with the invention of photography, then it was possible to take accurate measurements on photographic plates of the parallax that a star would be observed to have 6 months apart. If you measure January and July, the Earth has moved halfway around its orbit, 186 million miles across, and relatively near stars would seem to move back and forth ever so slightly against the background of more distant stars. So calculating this is all in your book in multiple places. If the star had exactly 1 second of parallax, 1/3600th of a degree, it would still be 3.261 light years away. And there aren't any stars that close. So any stars that we are actually going to see are going to wind up with a much smaller parallax than that, which is a major problem for the ancients, but not anymore, although we're always trying to refine the measurements. So this is the step 1 of the cosmic distance ladder of finding things, is being able to measure relatively nearby things using parallax. Cepheid variables. We jump to the stellar evolution program. And you remember that a solar type star, one like our sun with a mass of 1 solar masses and a luminosity of 1, when it gets near the end of its lifetime of its usable, burnable hydrogen, which takes about 5 billion years, the star will swell up and become a red giant and send out a shell of gases around itself, becoming a planetary nebula. Then it starts to brighten and move across the Hertzsprung-Russell diagram, which we'll see in just a moment. And as it goes across the middle, it goes through a period of instability where it fluctuates, getting brighter, dimmer, brighter, dimmer. And here this is a Hertzsprung-Russell diagram where we look at the absolute magnitude or luminosity, the brightness of stars. The brightest ones are up near the top, versus the spectral type, or essentially the color, where the blue, hot, purple ones are over here, yellow like the sun here, and the reddish ones over here. So if we make a graph like this, most stars fall along this pattern known as the main sequence, but that is not really a sequence as we talked about before. But when a star like the sun leaves the main sequence, it becomes a red giant in this area, then gets a little brighter and hotter as it moves across, and here's where it undergoes as a delta Cepheid, the prototype of this star, is doing now. It fluctuates in brightness and color, and that is what a Cepheid variable star is. Now here's another diagram showing that. Here's where the sun would have been on the main sequence, becomes a red giant, sends out a planetary nebula, becomes a variable across here. It wouldn't have killed them to add on just another inch on this graph so we could see that this doesn't go out of existence here, but actually comes back down and becomes a white dwarf star, very tiny, about the size of a planet. Maybe some are even as small as the Earth, some as big as Neptune, but planetary in size compared to the huge balls of gases that they used to be. So that's another whole story. But with the Cepheid variables, they're across here. This is where they undergo their fluctuations. Now, they do this over a period of a few hours to about 100 days, depending on how heavy and bright and how much momentum they have, and how the mechanism where the heat and light escape and then are trapped, and then it goes through a cycling process. That depends on how much material is in the star as to how long it takes to do that. The brightness increases faster than it decreases. So if you make a graph of the light curve of Cepheid variable, it looks kind of like a shark fin sequence of events with rapid rise, slow decay, rapid rise, slow decay, as the star is pulsating in size and brightness corresponding to the light curve that we see. Now, why is this so important? Well, it turns out that after we can measure roughly the distance to some of the nearest ones, we can work out a relationship between how bright that star really is and the length of its period of pulsation. We can figure out the absolute magnitudes, which are just another way of saying their luminosities, how bright they truly are, not respective of their distance, but just how bright they intrinsically are. That can be worked out from the light curve. And here is the period luminosity for the Cepheid variable. Once that's been determined, can you see how valuable that would be? All you would have to be able to do is to measure the period of a star that's fluctuating in brightness, which is fairly easy to do. Just take multiple observations and record it either with a photoelectric photometer or by visual means, which used to be done. It's fairly accurate. Once you've gotten the period of it, you read off of the graph how luminous the star really is. And then realizing that the brightness that a star has in the sky depends on two things: how bright it really is and how far away it is. Once we know how bright it really is, then we can figure out how far away it is. Here's the Cepheid variable luminosity versus period curve. For example, if you measure a particular Cepheid variable and you find that its period is 30 days, right out a month, and you read off the graph, you'll see that that star is something like maybe 12,000 times as luminous as the sun. Now that's kind of interesting in itself, isn't it? 12,000 times as luminous as the sun. That makes them easy to find. In other galaxies, if they were little dwarf stars, this wouldn't be much good because you could just about run a tape to it if that was the case. But in distant galaxies, if a star is 30 times as bright as the sun, they're actually easy to find. They stand out. So that allows us to measure distances to relatively nearby galaxies just by finding Cepheid variables, measuring the period, reading off of the graph, seeing how luminous it is, comparing that to how bright it is in the sky. We can easily calculate the distance, knowing that the brightness falls off with the inverse square of the distance. You've heard of the inverse square law. If something is twice as far away, then it's 1/4 as bright. So it's very easy to calculate the distance once we know that. Then, as I just said, I think I've already mentioned that. If we know the absolute magnitude or luminosity, then we can calculate the distance. There are other ways of doing this. Suppose we find a star in a cluster. And a lot of stars are still in clusters. They're all formed that way. But suppose we find one that's in a star cluster. We can make a Hertzsprung-Russell diagram of that cluster. And what's the one thing we know about all the stars in that star cluster? The same distance. So all of the stars in that cluster are already the same distance. So if we knew how bright any of them were, truly, we can figure out how bright all of them are, and we already would have known the distance. So we can compare one with the other, see what the Cepheid variables look like in that cluster, compare them with stellar type stars, and come up with the intrinsic brightness of any star in that cluster. So, and then once we compare that with how bright it appears in the sky, those are the factors we need. How bright does it look in the sky? How bright is it really? The third leg of the triangle is the distance. So that lets us calculate that from the two visual observations of the knowing the real magnitude or brightness and its apparent brightness in the sky. Sometimes astronomers, in their arcane ways, refer to this as spectroscopic parallax. Well, parallax has nothing to do with this, except that the parallax that we saw a few slides ago is a method of measuring the distance to stars. This is a method of measuring distance to stars. It doesn't involve parallax, but it's, you might call it a spectroscopic method with parallax-like results in that we are able to calculate the distance from that. So, but I'm warning you on that if you read about that in an article somewhere and you say, what in the world does that have to do with parallax? Well, the answer is actually nothing. Now, here's another interesting thing. It turns out there are two different kinds of Cepheid variables. Remember population 1 stars, the ones out near us in the spiral arms of the galaxy, like the sun? Population 1, sun, kind of rhymes. And then the population 2 stars are near the nucleus of the galaxy. 2, nucleus, and also the globular clusters that surround the nucleus. So there are two different kinds of stars, populations in a galaxy. And the Cepheid variables follow that as well. Now, as it turns out, we'll see that the calibration curve for measuring Cepheid variables was set up using population 2 stars. And then they tried to use it on population 1 stars and other galaxies, which led to errors. And we'll see how that works out in just a moment. Here is Henrietta Swan Leavitt, who in the 19th century was one of the great pioneers of theoretical astronomy and calculations and determining spectral classes. And half of what we did in one of the short course segments is basically due to her work. So she was one of the literally shining stars of astronomy more than 100 years ago. She was working at Harvard, used Cepheid variables, and measured the distance to the smaller Magellanic Cloud. Well, what's that? That's one of our satellite galaxies. You know, the Milky Way galaxy has 2 satellites, the smaller and larger Magellanic Clouds. We can't see them from here, but you can from the southern hemisphere. She found Cepheid variables in them and set up her light curve, the period luminosity, based on those. Well, they turned out to be population 2 stars, and we'll see what problems that caused. Then, a little bit later, Harlow Shapley, not Shapley, I don't know if he was Shapley or not, but his name is Shapley. He measured the distances to Cepheids in the globular clusters surrounding the Milky Way. Now those worked out all right because those were population 2 stars like the ones that Henrietta Leavitt used. The globular clusters around the nucleus are population 2 stars. So the curve worked for that. What was his idea? He figured we're inside the spiral galaxy. We're probably not at the center. How did he figure that? Well, We never had been at the center of anything, starting with all of the ancient beliefs knocked down one at a time. We weren't at the center of the solar system. The sun didn't go around the earth, neither did the other planets. So why should this be any different? It would be unrealistic to expect we were at the center of the Milky Way. Also, it doesn't look like we are. One of the things that John was referring to is observing the Milky Way in the summer and the winter. It looks different. It's a lot brighter in the summer because the nighttime side of the earth is facing in towards the center where most of the stars are. In the winter, we're looking out towards the edge, and it's just kind of a thin smattering of stars. It's a continuous band all the way around the sky, but it doesn't look like it's summer itself out in the winter sky going through Auriga, Gemini, and Orion. So he figured if he measured the distances to all the globular clusters, and that may sound like a daunting task, and it kind of was, but there are only about 100 of them. They're not zillions of them. There are about 100 globular clusters around the Milky Way. And he measured the distance to all of those, and he assumed that the common center of all of those was the center of the Milky Way, because they were all orbiting around the center of the galaxy. So if he could figure out the distance from where we are to the center of the globular clusters, that's the same thing as finding out how far we are from the center of the galaxy. So that was a major breakthrough. Here we are about a third of the way in from one edge. Here's the plain edge-on view of our galaxy. Here are all the globular clusters. And if you measure from here to here, here to here, here to there, measure all of them and take the average distance, that puts you right at the center of the galaxy. And that was how he was able to determine we were about 30,000 light years in from one edge across the 100,000 light year diameter of the galaxy. So about 33,000 light years from the center. Harlow Shapley. I've been a member of the Astronomical Society. In fact, we're married by the time he finally died. So he was one of the famous ones who, he didn't know me, but we overlapped quite a bit, actually. Then we get to Edwin Powell Hubble, another one of the greats of 20th century astronomy, for whom the Hubble Space Telescope is named. He, in 1924, used the 100-inch telescope at Mount Wilson Observatory near Los Angeles to measure Cepheid variables in the Andromeda galaxy, M31. At that time, there were still a number of people referring to it as the Andromeda Spiral Nebula, because it looks like a little fuzzy spiral cloud of light. And there were some people that thought that those were within the Milky Way galaxy. Several other kinds of nebulae that we've discussed and looked at, and these were just the spiral nebulae. But he, with that biggest telescope in the world at the time, he was able to tell that there were individual stars in it, which is kind of a giveaway anyhow. It isn't a nebula, it's something made up of stars. And he found some Cepheid variables in it, stars that had that sharp tooth sort of light curve pattern, and he was able to measure their periods and determine the distance to the Andromeda galaxy that way. He obtained a distance of 1 million light years, which made it so far away there was no way it could have been within the Milky Way galaxy, which is only 100,000 light years across itself. So this is something 10 times farther away than the size of our galaxy. So it's made it very obvious that this was another galaxy like ours. About that time, people stopped referring to the Milky Way as the galaxy, as if it were the only one. So now we're just one galaxy out of probably a trillion or so. Herschel had that idea a couple of hundred years before. He called these spiral nebulae island universes. He kind of had the idea that those were spiral galaxies of stars. Now in 1952, and I actually remember this happening, I didn't understand it at the time, but I remember the headlines in the paper. They used to be print science articles, and like on the front page if there's an eclipse or something. Turned out universe doubles in size overnight. Okay, That certainly sounds interesting, and my parents had no way to explain that to me, and I couldn't figure it out, so it took many years before I knew what they even were talking about. But what it turned out to be was that Hubble had been using the type 2 Cepheid variable curve that Henrietta Leavitt worked out, and the ones he was actually measuring in the Andromeda galaxy were type 1 Cepheids out in the spiral arms, which are a whole lot brighter. So since the type 1s are a whole lot brighter, he thought they were nearer than they were. Once he realized how bright they actually were, and to look as dim as they were, it had to be 2.5 times farther away than he originally thought. So it was, that universe went to, the nearest galaxy went to 2.5 million light years instead of 1 million once that got worked out. Okay. Similar kind of stars, RR Lyrae variables. These variable stars all have kind of peculiar looking names, and they're usually named after the prototype star, the first one that was discovered or extensively studied. And variable stars have their own system of nomenclature, which we won't get into tonight, but RR Lyrae is a variable star of this type. They have a very distinctive light curve, kind of like a Cepheid variable, but with a distinctive quirk to it. They go down slowly, rise rapidly, go down slowly, rise rapidly, but at the bottom there's a little hiccup, like it's getting ready to start back up and changes its mind and goes back down. So if you find one that has that little notch in it, kind of looks like a bad electrocardiogram here, if you find one that has like that, you know it's an RR Lyrae variable. Now here's the neat thing about RR Lyrae variable stars. They're just as bright as the Cepheids. They're right up there at the top of the Hertzsprung-Russell diagram, so they're very easy to find in other galaxies. On top of that, they're all the same absolute magnitude or luminosity. You don't have to set up a curve like we do with the Cepheid variables with relating the period to the luminosity. They all have an absolute magnitude of 0.6. So you've already done that part of the job. All you've got to do is find one, compare it to the 0.6 magnitude to what it looks like in the sky, and do the calculation with the inverse square law to get the distance. So they instantly give you a calculation of the distance. So these are, I'm pointing out again, they're among the most luminous of stars, right at the top of the diagram, so they're easily found in other galaxies. And for that reason, they're known as the yardsticks of the universe, because we use those to measure distances. Okay, a little sidetrack here, the Doppler effect. We can't go any further in this without understanding how the Doppler effect works. Everybody knows how this works for sound waves. If you pull out in front of a truck and he honks his horn at you, as he's approaching you, the pitch of the sound of the horn is rather high, and as he zips past you, barely missing you, you hear the pitch of the horn drop. That's because the sound waves, when the source is coming towards you, are compressed closer together, and so the waves hit your eardrum more rapidly than they would if the source were standing still. And as they're receding from you, the sound waves are stretched out, so when they come back to you, they're spread farther apart. They hit your eardrum more slowly at longer intervals, and you perceive that as a lower pitch of sound. So everybody knows how the Doppler effect works. It works for light just as well. If you have a star, let's say it's a yellow star and it's stationary, it's of course going to look yellow. If that star is approaching you, then the light waves are bunched closer together, and it looks like what a blue star would look like if it were sitting still, because blue light waves are closer together than yellow ones. And so you can do that two different ways. You can either have a blue star, or you can have a yellow star rushing at you, compressing its light waves together, which makes it look blue. And then if a star is receding from you, that same yellow star, its light waves are stretched out, and the light coming to you has a lower pitch, just like the lower pitch sound from the horn of the truck. and that moves it towards the red end of the spectrum. So that's the Doppler effect as applied to light. Now, same is true with not just a star, but even a galaxy. It's made up of stars, so the light waves are either bunched together or stretched out, and we can tell whether a galaxy is moving towards us or away from us. So all of the light, not just the maximum wavelength of each star as we were looking at before, determines the color of the star, but not just the maximum, but all the spectral lines. Remember the lines we were looking at when we had the demonstration set up here a few months ago? We saw that rarefied gases exhibit line spectra, and even compressed gases had dark lines crossing their spectra, which we can use to determine what elements are there and then roughly what proportions. So those are the spectral lines. Now those lines get shifted back and forth as well when a star or galaxy or whatever is moving towards us or away from us. They get shifted by an amount that's related to how fast they're moving. Related in one of the most gorgeous equations in all of science. It's so simple, you kind of wonder if it's even true, but it is. The shift in the wavelength, which is easy to measure. You can do that in the lab, you can do it at the telescope. When a spectral line is shifted one way or the other, that's what this is, compared to what the wavelength of that line is supposed to be if it's sitting still in the lab. That little fraction, the shift over its rest value, is the same fraction as how fast it's going compared to the speed of light. Isn't that amazing? Beautiful equation. So we can just measure the shift, what it's supposed to be, and instantly calculate the speed that something is moving as a fraction of the speed of light. Now this equation only works when the speed of recession is considerably smaller than the speed of light, like 10% or less. You know, if you're got something that's going 90% of the speed of light, we have to use a more complicated version of the equation. Here's some actual spectra. Here's the comparison. This is done, I would say, in the lab, but they actually take it into the observatory and record the spectrum of some known substances right on the photographic plate. The same one they're taking. This is a quasar, 3C273. And here are three of the lines from hydrogen, beta, gamma, and delta, corresponding to the 4 to 2, 5 to 2, and 6 to 2 transitions of electrons. So we went over that before. Here they are in that quasar, moving, instead of hydrogen beta being here, it's way over here. And the gamma is moved from here to here, delta from here to here, towards the red end of the spectrum. Well, what does that tell us? That quasar is moving away from us at a considerable speed. And it turns out to be about 16% of the speed of light that particular quasar is receding from us. Here's another one from one that's receding at a speed of 20% of the speed of light. Now I can do this one in my head. 20% of 5,000 is 1,000. So it shifted from 5,000 to 6,000. So from sort of blue-green to yellow-green across there. And all of these others you can see go up by the same amount, by 20%. And so all those spectral lines are easily measured, and we can tell that whatever this object was is going away from us at 20% of the speed of light. Now, if things get going faster than that, like 50% to 90% of the speed of light, then we have to use a souped-up version of the equation, which is down here. So instead of just V over C, it's 1 plus V over C over 1 minus V over C, all under square root minus 1. Now if you look, if you put in a very small value for V, like 0.1, this equation reverts to that one. So if this was, say, 1.1 over 0.9, suppose the V is 0.1 speed of light, so 1 plus 0.1 over 1 minus 0.1, that's 1.1 over 0.9, that's about 1.22. If we take the square root of that, that's 1.1 minus 1 is 0.1. So we're back to the other equation again. You can always use this one. If you don't need to, it's just a little wasted effort. But if you do need to, it doesn't lead to mistakes like this one. Sometimes this will tell you something's going faster than the speed of light. And when you do that, you figure, uh-oh, better use the other equation. Okay, yeah, here's one that's really moving. Here, spectral lines are all twice as long as they should be. 2,000 goes to 4,000. 4,000 goes to 8,000. Well, if you use the simple equation, that would tell you that it's going away 100% of the speed of light. Well, it's not. If you use the better equation, the more complete one, that tells us it's only about 60% of the speed of light. You know, that's still flat cutting out, but it's at least doesn't violate any basic rules. Okay, here's somebody that you may have heard of and you may not. He's sort of the unsung hero of cosmology. Monsignor Georges Lemaitre, a Belgian priest who lived in mainly the early middle 20th century. He observed from Hubble's data as it was first coming in 1928 that more distant galaxies seemed to have a higher redshift, meaning it was moving more rapidly away from us. The farther away they were, it seemed like the faster they were moving. He didn't have a huge table of data, couldn't make a graph or derive an equation for it, but he was the first one who noticed and wrote down that the more distant galaxies were receding more rapidly. This was not a popular idea at the time. He wrote it up, and guess who he sent it to? At the time, today you'd send it to Stephen Hawking. Back then, he sent it to Albert Einstein. And Einstein, turns out, didn't like his idea at all. He liked the idea of a stationary universe, nothing expanding. There must be some other explanation for this. So he filed it away. But he didn't lose it. So he couldn't do a graph or come up with an equation, but he explained this in terms of an expanding universe. He proposed that the universe began long ago as sort of a primeval atom or cosmic egg, and that began to expand and form the universe. That was Lemaitre's idea in 1928. And this was 3 years before Edwin Hubble came up with essentially the same idea and started getting all the credit for it. Well, about that time, Lemaitre said, wait a minute, I came up with this before. And they said, prove it. So he got back in touch with Einstein again, who was gracious enough to say that, yes, he did send me that communication 3 years ago. I still don't think it's a good idea, but he did say it. So now he sort of retroactively starting to get some of the credit for proposing the expanding universe before anybody else. By 1931, Hubble and others by then had used Cepheid variables measuring the distances to lots of galaxies, and the spectroscopists, of course, had to measure the shifting of the lines and therefore calculating the speeds of recession of the galaxies. By then, they had enough to make a graph. That's the gold standard for science, is you get enough data to make a graph and you get a good correspondence from one variable to the other. That means you're really onto something. So they got a linear plot of velocity versus distance. And so the velocity is proportional to the distance or equal to some constant times the distance. There's the first Hubble diagram, or a reasonable facsimile. It was drawn on a napkin or something, the first one, but these are the data that he used to get the velocity of recession, remember it's receding from us, versus the distance. And you can see that there's a lot of scatter in the data, but most physical scientists would agree that this is a good correlation. And of course, it got better after that. The proportionality constant is now known as h sub 0, the Hubble constant. And it's the same as the velocity over the distance, the y over the x-axis, or the slope of the whole diagram. For individual galaxies, it's better to use the slope of the whole diagram because the individual ones scatter around so much you'd get 30 different values. But if you draw the best straight line and get the slope of it, that gives you a good value for the Hubble constant. So the Virgo cluster of galaxies, we know from other means, like Cepheid variables, lies at a distance of 38 million light years and is receding at a velocity of 710 miles per second. So a simple calculation, the velocity divided by the distance shows that the Hubble constant for this is about 18.7 miles per second per million light years. That's the slope of the graph. You can also express it in other units, kilometers per second per megaparsec. Then it comes out just below 100. The values have ranged all over the place for a lot of reasons, which we're not going to get into, but it's kind of hard to sample the universe. Nearby galaxies may not be doing exactly the same thing as the universe as a whole. So, and of course they did the nearer ones first because they were easier, but the values have ranged from about 50 to 100 kilometers per second per megaparsec. And the best current value is 71.4 kilometers per second per megaparsec. One of our members, a long time ago, about 30 years ago, Professor Albert Woolett at University of Memphis, or Memphis State then, made a humorous graph showing the variation of the Hubble constant over time. So from 1930 to 1980, which is about when he did it, the Hubble constant had changed quite a bit. And that's why I say that the membership of the Astronomical Society has been more constant over the years than Hubble's constant, because we're always about 50 members no matter what. So here's they even drew a best line, or supposedly. Once the Hubble diagram was developed, then extrapolation, that's the next thing a scientist wants to be able to do, is to measure over an easy to measure range and then extrapolate the line, hoping that it doesn't do anything weird when you do the extrapolation. So this allowed astronomers to find the distance to a galaxy only by measuring the redshift, which remember is easy to do. You take a picture of it and see where the lines are in the spectrum compared to the reference standard. You don't have to do any Cepheid variable monkeying around to see how far it really is. You just measure the speed. Then you can read off of the graph. Like suppose you find that the velocity is this. You read over to the graph and then down to the distance. And that's how we get the distance to the most distant galaxies, is assuming the Hubble diagram is correct beyond our means to measure an actual distance. We've done that in here and it looks okay, but if we go out farther and farther, we trust it to give us the distances for ones where we can only measure the speed of recession. That's a little risky, but that's kind of the best we can do. Here's an example. A galaxy, we measure the recession speed of 9,500 miles per second. Now, if you think about what that means, that is really going, that's more than the diameter of the Earth in a second. It isn't like the speed of light, which is like 7 times around the Earth in a second, but this is really moving fast. How far away is it? Well, we solve the Hubble equation for the distance, and we take the speed, 15,300 kilometers per second, divided by the Hubble constant, and we wind up with 214 million parsecs, which is 698 million light years. So that's way out there, almost 1 billion light years away, and there's no way to do that except by extrapolating a Hubble diagram. Here are a bunch of galaxies near to far with their red shifts, slight, more, and then the distances calculated out to way out. 1,220 million parsecs out there. That's billions. Okay, a little flashback before we finish up to last time, where we were talking about the beginning of the universe with respect to galaxies. After the beginning of the universe, there was probably only energy, probably in the form of gamma radiation, the shortest wavelength, highest energy form of radiation. But all others were present as well. If you want to interpret that as let there be light, you will have crossed over the boundary just a little bit, but it's not inconsistent, let's put it that way. After a few more seconds, some of this energy converted into matter. Remember Einstein's equation, E equals mc squared. We normally think of that as we convert some matter into energy, like in a hydrogen bomb or an atomic bomb. Figure out how much mass is lost, multiply it by the speed of light squared. That's how much energy is given off. It works the other way as well. If we put huge amounts of energy into a system, it can be converted into matter. And that's what happened after a few seconds from the beginning of the universe. The simplest things first, single proton nuclei, hydrogen, deuterium with a neutron in place, helium with 2 protons in the nucleus. After a few seconds, then a few minutes, elements 3 and 4 were probably formed in very small amounts. That's 4 out of the more than 100 on the periodic table got formed in the first few minutes of the universe. Then no more elements were made until much later, after new stars started converting hydrogen into helium, and then red giants, helium into carbon, and on down to iron. And then in the red supergiants, once we go past iron, a supernova explosion occurs, and then all the rest of the elements in the periodic table are formed in a split second. So all of those happened much, much later on, after the whole first generation of stars did their thing. And said that? Okay. Now, back to what can we learn from the Hubble relationship? What kind of cosmological implications are there? First one we can figure out with no trouble at all is the age of the universe. Anybody who's been to the 9th grade knows that distance equals rate times the time. And if we consider that the galaxies are moving apart from each other at a particular velocity, over a period of time they will have gone a certain distance. That's what the Hubble diagram is, isn't it? The velocity versus distance. And the time we're talking about is the time when the first pistol was fired and the galaxies started moving apart from that central location. If we solve for the time, distance over velocity. Well, that's the reciprocal of the Hubble diagram, isn't it? That's velocity over distance. Well, no big deal. All we have to do is take the reciprocal of the Hubble constant, and that will give us the age of the universe. Just take the 1 over h0, solve that, and here it is. It takes about a half a page of arithmetic and a lot of unit conversions, but there's no magic involved there. If we take the reciprocal of this, we'll get 13.7 billion years for when it started. And it's uncertain to 0.2 of a billion years, so plus or minus 0.2 out there in the first decimal place, based on the most reliable data we have up to the present time. Not 6,000. That's a number of people still use other ways of figuring out the age of the universe, and 6,000 I think is off roughly by a factor of 2 million, which is generally considered a serious error. So this is the Hubble age of the universe. There are other ways to figure it. Okay, now, why are all the galaxies receding from us and therefore from one another, with the most remote receding the fastest? Okay, as Lemaitre proposed, most likely we had some kind of an explosive formation of the universe. He called it the cosmic egg or the primeval atom, now generally referred to as the Big Bang. We'll see more about that in a minute or so. Caused the newly formed matter to fly apart from each other. Fastest ones have now traveled the farthest. If you look at a Hubble diagram, that doesn't mean that a galaxy, as it gets farther away, goes faster and faster. It doesn't mean that at all. All that is a record showing that the ones that were moving the fastest all along have gone the farthest, and the ones that weren't moving very fast haven't gone very far. You wouldn't believe how long I worried and thought about that before I realized how simple it actually was. It's not a history of a particular galaxy. It's a snapshot of all galaxies, and the fast ones have gone the farthest. Okay, the raisin cake model. This explains why wherever you are in the universe, it looks like you're at the center and all the other galaxies are moving away from you. If you go to make a raisin cake and you stir the raisins into the batter and then you put that in the oven, as the batter rises, the raisins separate from each other and get farther and farther apart. If you were a microbe on any one of the raisins in the raisin cake, wherever you looked throughout the batter, assuming you could do that, everything would be moving away from you, and the ones that were farther away would be moving away from you more and faster, no matter which raisin you were on. So wherever you are in the universe, all the galaxies seem to be receding from you as the universe expands, and as a result, you look like you're at the center with everything moving away. So as a result, from this, you can't really tell where the, quote, center of the universe is. Now, I put the center of the universe in quotes for a reason. A lot of people, I don't know about a lot, but some scientists maintain there is no center of the universe. Some maintain that the universe is infinite in all directions. And of course, if it were infinite in all directions, there wouldn't be a center. That would be nonsense. So here is where we, for briefly, cross the line into some parenthetical thoughts. There's the open parenthesis. About 3 slides later, we'll get to the closed parenthesis. An infinite universe, right, wouldn't have any center. Some scientists believe, and I emphasize that word, believe the universe had no beginning. Or, alternatively, it created itself from what they think of as perturbations in space-time. Everything, all the perturbations just lined up just right one day, and all of a sudden that led to the formation of the universe. And here a couple of the people who were involved with that thought. That can't be proven or disproven, and that therefore it's not really science. If you believe something, that has nothing to do with science. The Big Bang, or I'm equating that with creation, is the dividing line between nothing before and something after it. Pre-creation and the universe. Or, another way to look at it, between theology and science. They're two different areas. You know, when we're talking about how to measure the distance to Mars, that doesn't really get into deep philosophical things. But when you're talking about cosmology and how the universe started, I think that does. And it's natural to think about it, and I've thought about it, and I'm telling you a little bit about what I think about it. Here's some of my opinions here. Believe is not a scientific word. You either know something or you don't. Or you know that something has been proposed and it needs to be tested. Belief does not have a place in science. So if somebody say, do you believe in global warming? That's not a valid question because it's not a matter of belief. On the other side, you can't prove anything is by theology. Prove is not a theological word. You can't prove the existence or non-existence of God, for example. That's a matter of belief. They're two different sides of the line. Can you ever get science and religion together then? Well, I maintain you can. If you have a scientist who is unusually thoughtful and religious, sort of like Monsignor Lemaitre, or unusually scientifically informed theologians, which are even more rare, it's possible within the same person to reconcile these things. But don't count on it. And in fact, it's probably better to not make pronouncements in the other field. Could go into many examples where people don't follow that principle that are going on in our world today. But if you're a scientist, talk about theories and proofs and so on. If you're a theologian, talk about beliefs and things, but don't cross over. Each one has to know where their boundaries are. Scientists need to acknowledge that they can't ever figure out what was there before the Big Bang. There are some who disagree and are spending their lives trying to do that. But that's the other side of the line. What led to it? That isn't really science. So they're speculating, but no scientific experiments can be done. It's something they have to believe in, and then it's not science when you do that. St. Thomas Aquinas, back in the 13th century, he was a scientist. He was the one who came up with the first system of organizing plants and animals before Linnaeus came up with his binomial system of labeling all creatures, plants, and animals. He was also a theologian, and he got into the idea of causes. Anything that happens has a cause. Now that has a cause, and that has a cause, till ultimately you get to what he called the uncaused cause, and he had to leave it at that. Being a scientist and a theologian, that was still as far as he could go. So theologians going the other way have to acknowledge their limits as well, and that would include practically everything after the Big Bang. Once the theologians come up with the idea that God created the universe, then you have to turn it over to the scientists to figure out how and what led to what and all of that. That's not theology anymore. That's in the area of science. Galileo put it nicely. He said, the Bible is made to tell us how to go to heaven, not how the heavens go. And he got into a lot of trouble when the Pope at the time kept trying to tell him what went around what, namely the sun going around the earth, backing, ironically, the pagan Aristotle over their own priest, Copernicus. So they got into a really fine mess when they didn't follow this principle. Bishop Ussher figured out that the universe was 6,000 years old, adding up all the begats in the Bible. A whole lot of begatting going on, but it only added up to 6,000 years from the beginning to now. Here's kind of a little side thing to think about. 300,000 species of beetles in the world. God must have really loved beetles to make so many. Did Noah have 600,000 beetles with him on the ark? Just something to think about. So, if we make the separation, we run into no trouble. If we try to blend things and confuse them, then we do. Here's an example of a theological truth in quotation marks. In the beginning, God created the heavens and the earth. The details about all of what happened on each day were not intended to convey the theology, and they're certainly not intended to convey scientific truth as well. So like the story about why the bear has a short tail. I think everybody's heard about that. If you haven't, I won't spoil it for you, but it involves an unfortunate accident with ice fishing. Let's put it that way. Okay, here's the end of the parenthetical thoughts. You can't believe one thing on Sunday and something else the rest of the week. You become paranoid if you do that. It won't work. Truths do not conflict. True science does not conflict with true theology. If you think there's a conflict, then at least one of them is wrong. You hear a lot about science versus religion, or in this part of the country, particularly creation versus evolution. There's no need for that false dichotomy. Usually, for those people, the creation means a literal scientific interpretation of Genesis. Evolution means man descended from monkeys. So you're never going to get those two together. But that's not what either one says. So there are some things. With all that said, now we're back into pure astronomy again, almost. This is Fred Hoyle, who, yeah, well, almost, except for when he wasn't, then he got screwed up. He was a great scientist, but he let his beliefs system get in the way of his science. Now, Fred Hoyle, remember what we just went over about the stars converting hydrogen to helium, to carbon, down to iron, and then the supernova? All of those equations were worked out by Fred Hoyle primarily. Now, he should have quit while he was ahead, but he switched over into cosmology later in his life, and practically everything he said was wrong. For him, as an atheist, the universe couldn't have been created. It had to have been there all along. And if it was there all along, it was always the same. So as a young man, he believed that the universe was eternal and unchanging. What's that? Einstein went back and forth, and he seemed to take a lot of different positions depending on who he was talking to. So you don't really know what Einstein thought. But you had no trouble knowing what Hoyle thought. He was very outspoken. He apparently had no trouble with an eternal, unchanging universe. It was just an eternal, unchanging God that seemed to give him a lot of trouble. After the data of the expanding universe started coming in from Shapley, Lemaitre, Hubble, and the idea of an expanding universe, then Hoyle kind of changed his tune. He got together with Hermann Bondi and Thomas Gold. Gold, Bondi, that sounds like a itch powder thing, but anyway, they got together one night after watching a science fiction movie. I'm not kidding. They three of them watched a science fiction movie and came up with the idea of continuous creation. That the universe, okay, you win, it's expanding. However, it's still staying the same because matter is continuously being created and filled into all of the gaps between the galaxies as they expand. Kind of like if you have a big puddle out in the parking lot and there's a rain cloud right over it, the rain keeps filling in and allows the puddle to expand and still keep the same depth. So that was his continuous creation. Later on, he just started calling it CC so he didn't have to use the word creation. He had a radio program, sort of like the early version of Carl Sagan's Real Cosmos series. And on one afternoon, he really started going into Lemaitre and Hubble and referred to their ridiculous ideas of an expanding universe that actually had a beginning and called that the Big Bang. So he made up the name for it derisively, but it's the one that stuck. So that's kind of an irony there that he wound up naming it against his will. So he kept trying to modify his various continuous eternal universe theories, but what really seemed to do it in was the discovery of the cosmic background radiation by two radio astronomers, Arno Penzias and Robert Wilson, in 1964. That pretty much killed the steady state theory, because what it did was it discovered the cosmic background radiation that was the residue from the Big Bang. It consists of photons which escaped about 380,000 years after the beginning of the universe. This was called the combination era. Now, what does that mean? Well, remember, first just photons, then simple nuclei of atoms with electrons floating around freely, a plasma. Protons, electrons, some helium nuclei, more electrons, not combined because it's too hot. But after 380,000 years of expanding and cooling down, it got cool enough for the electrons to fall onto and join up with the atoms again. Well, that gives off photons. That's where these photons came from. That's a little shell. It's pretty small compared to the universe today, 380,000 light years in radius, if it was expanding at the speed of light, but that's a maximum size. So that's where they came from. They've lost energy since then. They were ultraviolet and visible at that point, but now they've cooled way down and have corresponded to energy radiating from something that's 2.73 degrees above absolute zero. Very, very, very cold, because it's had, nearly 14 billion years to cool down since then. And that's in the microwave region of the electromagnetic spectrum. Here's a graph based on Planck's law that Bill showed you a few months ago. If you know the temperature of an object, you can calculate how much energy it puts out at every wavelength. And that's the red line is the result of the Planck equation being plotted for an object at that temperature, 2.725 degrees Kelvin, or 1.871 millimeters in the microwave region. The actual black dots, can you see them on there? Okay, those are data points that have been taken of the cosmic background radiation. Some of them through the atmosphere from the Earth, but most of them from the Cosmic Background Explorer, or COBE satellite, that was sent up to determine this. And as you can see, all of the points follow the predicted line perfectly for cosmic background radiation that corresponds to the age of the universe at that distance with just exactly what the Big Bang would predict. Now, the very last things here, the ultimate fate of the universe. If the Hubble diagram were a perfectly straight line, the universe is open, because that means that galaxies are expanding away from the original explosion and will just keep doing so and eventually just go on out and fizzle out, spend all their energy. And some people call that the great whimper, was the end of the universe. It would just entropy out, fizzle out, and stop. If the line has an upwards curvature out at the right upper end, then that indicates that the universe is slowing down in its expansion, possibly caused by invisible matter or the mass of neutrinos or something. Now, I used to worry about that too. If it's going out farther, doesn't that mean it's speeding up as it gets out farther? Well, that's not an individual galaxy getting out farther. What that's telling you is that if the end of the Hubble diagram is curved up, that means that long ago, because we're looking back in the past, the galaxies were traveling faster than they are now when we're looking closer at the more near ones, and things have slowed down. So if the universe is slowing down in its expansion, which is what this would indicate, then that might cause the universe to stop expanding and maybe even fall back on itself, the big crunch, as it was referred to. And then that led to the idea, well, if it fell back on itself, could that cause another Big Bang and it could just do it all again? Well, the atheists jumped all over that, because then they said, okay, you got us this time because, okay, we found that the universe as we see it now definitely had a beginning 14 billion years ago. But that doesn't mean that that's the only universe. This could be the umpteen zillionth one, and it could have been doing that from all eternity. So then they were happy about that. So the oscillating Big Bangs, Big Crunches, George Gamow was one of the leading proponents of that, along with Hoyle, of course. Okay, is there enough matter in the universe to slow down the expansion or even reverse it? So that was the big question towards the end of the 20th century. Careful measurements of distances where you don't have all that scatter and recession velocities, that would tell the story. And that was one of the main reasons the Hubble telescope was built, was to answer that question. Okay, we can call the change and expansion of the rate of the universe over time as Q0. And it was all thought to be deceleration, various degrees of slowing down. And here are 4 different graphs of a Hubble diagram with the either going out straight, if Q equals 0, no deceleration, and the universe is open, and we'd have a big whimper at the end. If it's between 0 and a half, there's some deceleration, but not enough to stop it. It would keep going. The borderline case is Q is a half. It might slow down enough to even stop, but not enough to fall back in on itself. Marginally open. And then if Q were greater than a half, then there's full deceleration. It would come to a stop and then fall back in on itself, collapsing universe altogether. So that was the question when Hubble went up. Which of these 4 was it? Or was it any of those 4? Well, the answer turned out to not only be no, but hell no. The universe is not slowing down. The Q is less than 0, negative out here, which means that the expansion of the universe is actually accelerating. Now, I remember when this first came out, I told my astrophysical chemistry class about that, and one young lady was looking around and acted like she wasn't paying attention. And then she asked the question, said, Dr. Busler, you know how at the beginning of the universe there was this spectacular beginning with the Big Bang? I said, okay. Don't you think that maybe God at the end would have some kind of a spectacular conclusion to the universe rather than just letting it fizzle out? And I certainly couldn't argue with that. And that's what Jeremy is going to be talking about, among other things, after a brief intermission. And we hope he can shed some dark on that. Okay. So.